Hey, hello and welcome back, everybody. Moving on to section 6.2. This is called finite difference methods. You've probably heard about it before. In fact, if you took my other course with the book Ordinary Differential Equations Done Right, we also use this method to solve boundary value problem ODEs. It's the same sort of method, it's just in PDEs. Obviously, you can perform finite differences in multiple directions instead of just one. And heuristically, I've got this little statement about really what we should think about with finite differences. They're kind of the converse to the continuum limit. So all the way back in section 1.1, we actually discovered this thing called the continuum limit, which you can use to construct PDEs, at least thinking about problems physically by kind of considering every physical dimension as a collection of nodes which influence each other. In fact, I guess you could go in like 2 dimensions because it's PDEs that we are working with, right? It's a collection of nodes or some mesh or grid, however you want to think about it, and they're all kind of connected to each other and they all influence each other. However you may represent that physically. And so all of these connections between all of the nodes that show up here, you take a finer and finer mesh and you end up finding partial derivatives or higher powers of partial derivatives through that mesh. That's called the continuum limit if you can actually pass to an infinitely small spacing between these nodes or infinitely many nodes. And in reality, finite difference is just opposite of that. So instead of creating a PDE from this like physical understanding of finitely many nodes, we're just going to try to approximate PDEs that maybe start out with a partial differential operator inside of them. And we're going to replace the partial differential operator with finitely many nodes that all interact with each other. So it's just kind of the opposite direction of that continuum limit. So that's what I've described here as kind of the reverse direction of the continuum limit. And what that's going to do for us is it's going to convert, an infinite collection of unknowns to finitely many. Finitely many being each of the nodes, right? So in the real world, a continuous process has infinitely many elements to it, you could say. But when you discretize that, you get finitely many. So we're going to define our operator that we're actually worried about. This is going to show up in all sorts of other areas of math as well. It's called the forward finite difference operator. And unfortunately, it uses a delta. I've got this remark here that says PDEs use delta for both the Laplacian and finite difference. You just kind of have to get okay with it and use context clues to figure out which one is which. We've got this operator delta sub epsilon. You'll sometimes see it as delta sub h, delta sub delta x, all sorts of random stuff you'll see in that subscript. But this operator, when it hits x, or f of x, so it's going to hit f of x, it's going to shift x by epsilon. It's also going to subtract where we started. Right? It's a finite difference because we've moved a finite amount, and we're calculating the difference by how much we've moved. So then you can construct an approximation to a derivative out of this, right? Because I could just write an epsilon underneath that, and that's really close to the difference quotient for the derivative. You can also take higher powers of this, right? If I take higher powers of this over epsilon to the n, that's kind of this operator here. If you want a closed form calculation for what higher powers this operator would do, we have it here. There it is. So that's what closed form higher power calculations of this operator do. And what you get is an approximation of the nth derivative. And so basically every time we see a partial derivative, let's say this is partial x to the n, we're going to replace it with this. Now I know that looks scary, but it's actually easier to solve because there's only finitely many terms there instead of the derivative. So every time we see a partial xn, we'll replace it with this sum. Obviously when n is small, the sum is easier to understand. You just kind of memorize what it looks like when n is small. You don't really worry with that arcane notation of the sum. And in fact, in partial derivatives, we're going to be using the finite difference operator or partial finite difference operator where I'm actually specifying the direction that we're performing the finite difference in. So I'm going to use delta sub xi epsilon. This is the one that's going to perform finite difference in the xi direction. So you can think about like this ratio, delta sub xi epsilon over epsilon to the nth power is approximately the nth partial derivative in the xi direction. So that's our finite difference operator and approximations to the derivatives. And here's examples where I said kind of in low power, right? Working in powers 1, 2, 3, and 4. You actually kind of just memorize what these look like. You don't really use that summation. In first power, what do you know? You get the difference quotient. That should look like what you've been working with since calculus 1, maybe even pre-calculus for some of you. In the second power, we get the following. So really what's going on here? Well, epsilon squared is no surprise for the second power. But what's going on in the numerator? We really do a few things on all of these. Notice that this should really be thought of as a plus 0 epsilon on the right. That's a plus 1 epsilon. So we're really going from 2 to 1 to 0 and epsilon, how much we're shifting forward. And then we're alternating in plus, minus, plus signs. And then these coefficients of 1, 2, 1 are Pascal's triangle. Let's just write out Pascal's triangle so that we remember what it looks like and we can start to compare. These are also known as the binomial coefficients, right? There's Pascal's triangle for us. Let's see if this works on the next line. So now I'm looking at 1, 3, 3, 1. 1, 3, 3, 1. There they are. And we also have alternating signs of plus, minus, minus. And then we have descending coefficients on epsilon. So we have 3 epsilon, 2 epsilon, 1 epsilon, 0 epsilon. So those are kind of the patterns that you start to recognize in these finite differences. And let's see it one more time with the 4s. Pascal's triangle of 1, 4, 6, 4, 1. We have alternating plus, minus, plus signs. And finally, we have descending coefficients on epsilon of 4, 3, 2, 1, 0. So those are really the patterns, and I do describe those patterns in words there. That'll help you figure out how these finite differences work in really any number of orders, right? You could immediately ask me the question of what is delta epsilon over epsilon to the 24 power, and if I had the 24th row of Pascal's triangle, I would probably be able to compute that for you. It's technically 25th because you start on the first row that corresponds to power 0, but you get the idea. So let's look at an example, make sure that this actually works. It's one thing for me to tell you that's what it is, and it's another to see it in action. So let's estimate the third derivative, cosine e to the x at x equals 1. Well, we can estimate it for an epsilon as 0.1. I write out the finite differences. That's me doing 1.3, 1.2, 1.1, and 1. My values of x. There's my alternating plus and minus signs. And then I have a 1, 3, 3, 1 from Pascal's triangle. There's 0.1 cubed in the denominator. This comes out to 28.3734. If I make epsilon a little smaller, maybe 100th instead, like 1.03, 1.02, 1.01, and 1.00, and 1 millionth it looks like there, we get 27.9975. If I make this even smaller, make epsilon 1,000th, 1.003, 1.002, 1.001, and 1, and then however many zeros that is, 27.413. You can make epsilon even smaller if you wanted to. 1.303, 302, 301, and 1. And so many zeros in the denominator, and you get 27.3516. Now, with that said, if you wanted to just go ahead and calculate the third derivative, you sure could. It's just a few chain and product rules. And there it is. You evaluate that at x equals 1. Well, you could get a purely mathematical expression for it, but if you decide to look at the numerical expression, it's 27.3447. So we're getting pretty darn close. Our finite difference methods is doing a pretty good job of approximating the derivative for us. So let's actually do it, describe the finite difference approximation method. It's actually a pretty tricky method. We're gonna have a shorter video today, but in the next video, which unfortunately you'll have to wait like a week for, but in the next video you'll see this in action. So we'll try to get used to actually doing this. It's really much more of a coding exercise, and so it doesn't translate too well to the textbook, but I'll do the best I can. So in the definition, I do have a nice step-by-step process here. We're gonna go through the step-by-step process all the way through today, and hopefully we can make a little bit of sense. So let's just start out with our lovely PDE here, which basically consists of some collection of the spatial coordinates and all of my derivatives of my solution equal to 0. And then maybe I have some boundary data that corresponds to, kth derivatives of my solution. The computation of an epsilon finite difference approximation is going to be the following step-by-step process. So what we're going to start with is actually an epsilon, because we're a PDE and x is an R, omega subset of a d-dimensional space. That means that there's d different directions we could take derivatives in, so d different directions we could take epsilon derivatives in, or epsilon finite differences in. So we're thinking about actually choosing epsilon as a vector of d different epsilons, so possibly different positive numbers. Put quotes small under this, small positive numbers. And they're going to correspond to the different d dimensions of x. Like how much are we going to do a finite difference in each of those d directions? So in step 2, what you can do is you can approximate your gradient, which is a partial derivative in each of the d directions. You can approximate it by what I'm writing here is I've got this tilde over the gradient, and that's because it looks like an approximation symbol. So a tilde gradient sub the vector epsilon, I'm saying that's really this approximate gradient that's constructed. So we've got an approximate gradient constructed from partial finite difference approximations to the derivatives, to the partial derivatives. There's a vector of approximations to the partial derivatives. And what you can do with that is you can play games, and you can take, if those are a bunch of outer products of the regular gradient, you can take just as many outer products of this gradient. You can calculate the higher powers of your approximate gradient. So that's really quite useful, that because you're constructing vectors out of these, you can still perform these outer product calculations of the vectors and get higher powers of the approximate gradient. So what that is basically allowing me to do is, at the end of the day, I'm going to replace all of these gradients, even that one, with their approximations from the finite difference operator. Now, with that said, you also have to construct a discrete domain. So here I'm writing omega sub dis. So I'm going to call this the discrete domain from now on. Omega sub dis, discrete domain. This is going to be the collection of d-dimensional points, so x's, that are constructed out of epsilon z. So these are really the epsilon I steps in every direction. And of course, the discrete domain will just be those which were already in omega, right? So I'm starting with my regular domain omega, and I'm going to ask myself, now which ones of these epsilon steps in every direction line up with regular omega? Let's draw a picture over here. Suppose that omega is some beautiful set. And suppose my epsilon z, so epsilon z's are also known as lattices, right? Because I'm taking epsilon steps in specific directions. So let's suppose I'm just taking a bunch of steps of an amount epsilon 1 and another amount of steps epsilon 2. So that's an epsilon 2 amount of a step. All you do is you fill this lattice in. And you can imagine that those should actually lie in a grid. I didn't do a great job of actually drawing them all out. But you fill the lattice in, and then you take only the points of the lattice, the epsilon lattice, that actually lie inside of omega. This is the discrete omega. Okay, so all of these that were already inside of omega, we're going to keep those, and we're going to toss everything else out. This is going to be the discrete domain. So omega dis. It's discrete because there's only finitely many points in there. That's really what's going to solve our problem for us. We're doing computations on finitely many points now. So there can only ever be finitely many points in this discrete domain. Now you do the discrete boundary as well here. I forgot the boundary. And what we're looking at on the discrete boundary is that we're basically going to be looking at every one of these lattice points that's exactly 1 point away from the discrete domain. So you're going to move 1 point in any direction away from my lattice. And as long as I can find a point out there, that's going to be what I'm calling the discrete boundary. So there's the discrete domain and the discrete boundary. Once again, there's only finitely many points here. And you can imagine as I put more and more nodes into this discrete area, making epsilon smaller and smaller, I'm going to fill it in better and better. So that's kind of how we construct a discrete domain and a discrete boundary. I realize I technically have definitions here. They're really, really horrendous, but you can use them if you want to. This big old X right here, that's just a Cartesian product of those sets over and over again. But that's, visually, this is what you want to think about. What you want for omega dis and partial omega dis. That's really what you want to think, is visually. It's just partial is one extra step. What is the next round of points that isn't in omega dis, but it's only one away from omega dis. Now, this is useful because now we only have finitely many points in our space, and we have a notion of an approximation to the derivative. What we can do is actually construct what's called the finite difference equation, which is only going to be an equation of finitely many points. That x in omega dis and x in partial omega dis, or the discrete domain and the discrete boundary, this is finitely many points. Finitely many. That's great. That makes this a system. This is just a system of an equations, right? So this is just a system of equations. And computers are great at solving systems of equations. So it's really, really nice if you can pull off constructing this finite difference equation. It's really, really nice once you have it. You just solve a system of equations. So what does it mean to actually construct it? This is probably the vaguest step here, especially because I've put some subscripts here as plus minus. So what do these subscripts mean where I'm saying plus minus? Let's scroll down a little bit. So the finite difference approximations, plus minus epsilon, have the sign modifiers, and they're defined as where you put a plus minus before epsilon 1, plus minus before epsilon 2, plus minus before epsilon d. What we want to think is that while delta sub epsilon is the forward finite difference operator, delta sub minus epsilon is the backward finite difference operator. And it's sometimes useful to work backwards instead of forwards, and I'll describe why right now. So let's go back to some version of, suppose this was omega, and suppose I also have omega, the discrete omega, and the boundary of the discrete omega. Well, then the finite difference operator, this kind of delta epsilon, is going to compares 2 points. Right? It compares f of x with f of x plus epsilon. So let's say that it compares this point, then it compares the point to the right of it. That's perfectly fine until you run into a boundary value, in which case you can't compare it to anything to the right. Boundaries on the right can't be compared to anything. Right? If I move to the right, I'm already at the boundary. I move into no man's land. There's nothing out there. And so what you have to do instead is you have to move to the left. You know, from the right boundary, you have to move to the left. That's a negative finite difference. So you need the negative finite difference to solve your problem if you're on the right boundary. But if you're on the left boundary, then everything's hunky-dory, right? In the left boundary, I can definitely just move to the right, and then I'm good. But in partial derivative land, you can also move up, right? So if you're at the lower boundary, you can move up and compare two nodes, finite difference upwards. But if you're at the upper boundary, you have to move down, and you need the negative finite difference. And so you have to make this choice at each boundary point, right? It doesn't matter on the interior, but it's right at the boundary. You have to make this choice that you make sure you choose the right collection of plus minuses to stay in the domain. Okay, and you can set up a computer to make sure that it does it. You just have to make sure it checks all the cases, like, oh, am I moving to the right where there doesn't exist a point? If that's the case, then do this other thing. So you have a lot of if-then statements sitting behind your computation. But that's kind of important, is that you need to stay in the domain. So you're choosing plus minuses on these epsilons depending on where you are in the domain. Now, if you're wholly in the center of the domain, don't worry about it. You can definitely move to the right, and you can move up super easily, right, when you're in the center of the domain. So it's not really a big deal. It's around the boundary that you care. But that will show up everywhere, right? Because the boundary is really close to the discrete omega, and certainly the boundary shows up right there. So you do have to pay attention about your signs on the epsilons when you construct this finite difference equation. Now, what's even more important than that, or I guess maybe equally important, is like, what does it mean to take values on the boundary now? Because our boundary has changed, right? We knew the value, kind of our PDE gave us the value around the true boundary itself. We don't have the true boundary anymore. We have this partial omega discrete. These points may not actually align with where the GKs originally were. So what we have to do, maybe let's zoom in on a boundary. Suppose that this was the original boundary. And now let's suppose that these points are my discrete boundary. They aren't on the boundary. They sometimes may be on the boundary, but they sometimes may be just outside of the boundary. You have to define this new collection of GK. So GK tilde at X is going to be defined by, you just find the closest point on the boundary and you define it to be GK at that point on the boundary. So you do that with all of these. So you kind of project them to the closest point to the boundary. Of course, as you put more and more nodes in there, those are going to get closer and closer to the actual values. But that's all that this is defining. It's saying, hey, we're going to project them to the boundary and let them take the value on the original boundary, even though they don't actually exist there. So that's definitely the trickiest portion. Like part 4 here, super hard. You're going to love seeing it in examples. That's really going to save you here. But we'll move on from there. In step 5, we've only got finitely many points in the finite difference equation. So even though this doesn't look like it, this truly is a system of finitely many equations. we'll say it's a system of, m equations with m unknowns. And in fact, it's usually a system of more than n. So there's m or more. You can make more equations in there, but you have more equations than unknowns, which means you can solve for those unknowns. What are those unknowns, by the way? Those unknowns are the approximate values for unknowns are phi x when x is in omega dis, the discrete omega. So you're going to solve for the value of phi at those specific points. So you just go ahead and find a computer, numerically solve those unknowns, and then you get your values of phi, but specifically only at this discrete set. Now, if you want them over the entire set omega, you can use what's called an interpolation procedure. If you've never encountered those before, just go ahead and Google them. We're not going to get into them too much in this book, but if you took a numerical methods class, it's a pretty important part of it. But you end up using an interpolation procedure basically to interpolate that set into the full omega. And that'll give you an approximate solution of PDE kind of everywhere. So that's really what we're going to do. You can see I'm moving into the example there, so I'm not really going to move all the way to that example right now, but I will describe what this paragraph that's kind of sitting at the end here states. I say that, steps 1 and 2 are pretty straightforward. You're just kind of choosing your amount that you want to shift everything by, the epsilons. Step 3 and 4 have the nuance. So this is defining omega dis, partial omega dis. Maybe not the most nuanced, but a little bit. Step 4 is really very nuanced. This is constructing the system of equations. And then in 5, that's kind of the computer's job. But if you have a nonlinear set of equations, I would point you towards Newton-Raphson as a method, but there's other kinds of root finding algorithms like gradient descent would also find your root in some cases. If they're linear, if everything starts at linear, then you don't even need these methods and you just invert a matrix. But when they're nonlinear, so you have nonlinear PDEs or something, then you'll need an algorithm that'll approximate it for you. And then, like I said, interpolation procedures are kind of a study in their own right. So we're really only scratching the surface of numerical methods, and use this, section as well as the next section on Galerkin methods just to kind of decide, hey, do I want to take a numerical methods course? Because that's what you're going to be doing. You're going to be doing a lot of things similar to what's going on right now. And the lecture is probably better than I am at describing them. So that's what I want you to think for now. In the next class, we'll actually get into what approximating this way looks like. I'll see you then. Bye.